We are going to compute the area under a function f of x equals x squared plus 1 using Riemann sums on the interval 0, 1. So first of all, that's a lot of terminology, and if you've made it this far in your calculus class and you're talking about Riemann sums, or if you're in the calculus 2 class and talking about Riemann sums, yeah, we've come quite a way, and you'll see that this has an awful lot of machinery involved in it. So first of all, that horrible machinery is gearing you towards doing something exactly what it says under here. I have a function f of x, which is x squared plus 1. And then what we're going to do is we're going to compute this area from 0 to 1. What that area ends up becoming is, basically what that is we have a nice fancy symbol for that. The integral from a to b of f of x dx is the crazy symbol that we're going to use. That is representing area under a positive function. By drawing it, I made sure that my function is definitely strictly larger than 0. It has no real roots. It has two complex ones. So, and then the machinery of what Riemann sums is going to do is this. It's going to say it's the limit as n approaches infinity of the sum from I equals 1 to n of f of x I star times delta x. And that seems like a whole lot of hot mess at first. But what this is saying is we have to remember whatever these symbols mean is it's computing the area under this curve. So to do this, I'm going to use right-hand endpoints. So to do that, basically what I need is, I know that my interval I is 0, 1, and my function is f of x equals x squared plus 1. The first thing I need is delta x, which is b minus a over n, which in our case is 1 minus 0 over n, or delta x is 1 over n. This is one of the most common mistakes, is forgetting the delta x, and then you're missing one of the powers of n, and then things don't work out, and you get an infinite limit because the powers aren't right. So don't forget this guy. So the next thing I need from that is my sample points. I'm going to use right-hand endpoints because I'm pretty sure this is what Riemann does, or classically this is the nicest formula for me, and it's classically what I was taught with and what I'm going to use. So using right-hand endpoints, this is equal to a plus delta x times I. And for us, so that's 0, a is 0, plus delta x is 1 over n times I. So this says xi star is I over n. Basically what we're doing is we're chopping carrots and we're chopping onions and we're chopping celery and these types of things, because when I want to make soup, I'm going to have to put it into that big machinery and stir the pot eventually, but I don't want to put whole carrots. That's not how we eat soup. We're going to prep it first, we're going to chop everything up, we're going to find out what I want, and then we're going to put it into this pot and stir it. So this is still not exactly what I want. I need delta x, I need f of xi star, not just xi star. So now I need f of xi star. So the next thing I need to cut is the potatoes. So having those two things, I now need f of xi star. And this is where, depending on what they give you, you may have to use the binomial theorem or simplify everything and clean everything up before I put it into the pot. So this is f of, what's xi star? We figured it out, it's just I over n. And that equals, in evaluation, I put I over n wherever x is, just like I would put a plus h in the definition of derivative. So this becomes I over n squared plus 1, which is, I didn't have to FOIL because a was 0. This is I squared over n squared plus 1. That's still not what I need. Now finally I put them into piles closer together, and then I'm going to dump them all using the cutting board into the pot. So I need this times this. So finally, f of xi star times delta x is equal to I squared over n squared plus 1 times 1 over n, which is I squared over n cubed plus 1 over n. That's what we need. And now I can put that simplified expression by cutting everything into smaller pieces. We can now hopefully digest what's about to happen. I must be hungry. Therefore, the area from 0 to 1 under x squared plus 1 is equal to the integral from 0 to 1 of x squared plus 1 dx, which using Riemann sums is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x I star times delta x, but I've already prepped it. It's this guy times I squared over n cubed plus 1 over n. So do you see now, instead of having to compute that and put that into each step and carry the machinery around, why are you trying to put them in the pot and then cut stuff in the pot? Prep it ahead of time, and then it gets much easier. Now there's a lot of work. Now we're going to stir the pot. Here we go. So the first thing we do also is I need to have a limit that has everything with just n's in it so I can push n to infinity. There's still i's in there. Until I get rid of the closed forms for the sums of i's, I can't push the limit to infinity. So that's the next strategy, is distribute the sums onto all the terms, factor the n's out, and compute what these sums of i's are. So this is equal to the limit as n approaches infinity. Yes, we have to write that every time. So I'm going to do it. I'll go slow. So first I'm distributing the sum onto both. A sum of a sum is the sum of sums. It's a bunch of sums. I equals 1 to n of I squared over n cubed plus the sum from I equals 1 to n of 1 over n. So I distribute the sum, the sigma onto the sum. Now, strangely, this bothers you at first, but watch the tutorial video. This sum is, I is changing, not n, so n can come out of that sum. So the next thing I'm going to do is factor out the n's. The limit as n approaches infinity of 1 over n cubed times the sum from I equals 1 to n of I squared plus 1 over n, the sum from I equals 1 to n of 1. Now I use the closed forms that I'm pretty sure, hopefully your instructor's nice, depends on what's going on, but usually a lot of the time we provide these sums on the formulas. But either way, you have to memorize that the sum of this one is going to be c times n. In this case it'd be 1 times n, or just n. The sum of I, Carl Friedrich Gauss does at age like 5, is n plus 1 over 2. Then the sum of I squared is n plus 1, 2n plus 1 over 6. And then we can do a bunch more of those if you want to see. That's a whole other course and a bunch of videos, which we are going to do. Equals, I put those in there. The limit as n approaches infinity of 1 over n cubed times n plus 1, 2n plus 1 over 6 plus 1 over n times n. It's at this stage that we can tell we did everything right. This one or the last one. The degree, once I sub in for the closed forms of I, the degree of n should be the same on the top and the bottom, because this is limits at infinity and I'm pushing n to infinity. I'm going to pull the highest power of n out of the top and the bottom, and if it's an improper but the degrees are the same, it will converge to exactly the value which is the leading coefficient of the top and the bottom. Long story short is you should know how to do limits at infinity already, and the strategy is always notice that one of the n's first of all will cancel, and one of them can cancel here because n cubed is n times n times n. So here's how I clean this up, but it's a check. The degree should be 3 on the top when you use the closed form and n cubed on the bottom, and here I got degree 1 and degree 1. So the degrees match on the top and the bottom. And then that means I'll get a finite number. Otherwise something will go wrong and you'll either get 0 area or an infinite area, which can't be true in this scenario. I like to write it like this. The limit as n approaches infinity of n over n, n plus 1 over n, 2n plus 1 over n, and I forgot, I don't care about the 1/6 in the first term, so I'm taking the 1/6 out, and then I'm distributing the n cubed onto 1 power each. Nobody likes to manipulate, but I'm allowed. N cubed is n times n times n, and I put it over 1 each. Why? First of all, one of them is going to go away. And then we also had plus just 1 because there's one already canceled. So by doing that, now I'm going to just use the reciprocal functions. Now I'm going to push n through the top and the bottom in all of these terms. This is equal to 1/6, the limit as n approaches infinity of 1 plus 1 over n times 2 plus 1 over n plus 1 still. The reason I've done that now is because we're going to infinity. These are 1 over n's, both go to 0. So I get my finite number. This is 1/6 times 1 plus 0 times 2 plus 0 plus 1, which is 2 over 6 plus 1, which is equal to 1/3 plus 1, which is 4/3. I multiply by 1 to get a common denominator, and the area is exactly 4/3.